Okay, I will just begin. Hi, everyone. My name is Jeffrey Young. I work at Epic Games. You can find me around the internet as DuGNU. And I'm going to talk about or rant to you about what I think functional architecture is, which you may have noticed many of the talks at this very workshop have asked that question and offered answers, and this is my time to now offer my answer. Okay. Yeah, so disclaimer, I don't know. This is just my thoughts. This isn't a paper. Please interrupt me, argue with me. The goal here is to spur some discussion. So if you go looking at definitions of software architecture, and this is something that Michael Sperber also touched on, you will walk through the history of people really trying to define this very nebulous thing. So there is an IEEE standard definition of it that's on the screen. This is actually the old version. There's a new version from 2022, but that's paywalled. So I think it's kind of funny that a standard is paywalled, but I couldn't get it for the purposes of this talk, but I'll just read it to you. So is the organization, fundamental organization of a system embodied in its components, the relationships to each other and the environment, and the principles governing its design and evolution, which I think is a very comprehensive definition. That's not the only definition. There's several other definitions from Martin Fowler and Ralph Johnson. Ralph Johnson's a co-author of the Game of Ford book. So another common, and I couldn't find a attribution for this one, definition is an expert developer's shared understanding of the system design. So if you go ask an expert developer of on any system, hey, what's architecture? And they will say, it's my understanding of the system and how it's designed. And I think that what this is really talking about is it's talking about a shared vocabulary, which this website I'm showing is the functionalarchitecture.org website. Please go to it to raise its Google rankings or ask ChatGPT about it. And on that webpage, Michael and I guess me, because I try to contribute, offer a vocabulary for different techniques and patterns. And I think this vocabulary gets to some of the heart of the previous definition, the shared understanding. But this goes on. So more definitions, these ones are more recent. Some of these come straight from Martin Fowler now. Is architecture is the design decisions that are made early in the project. Maybe that one's part of this. I don't know. I wrote this. I was sleep deprived on a plane. Architecture is the stuff that's hard to change, whatever that is. And this one is from Martin Fowler in a 2014 talk. And he says, it's just the important stuff, whatever that is. Yeah, go ahead.
No, but I mean, so stuff that's hard to change, that's clearly too encompassing because I like in my last job, I had to change a data structure that had blown out of proportion, and that every part of the system was touching. Okay, yeah. I don't consider that data structure to be architecture.
No, you didn't want it to be architecture.
But it was.
No, but that was just the data structure. That's not architecture. Like, it shouldn't be anyway.
Right. But so my point here is, let's accept this definition.
Yeah.
Okay, what does then functional that mean?
Yeah.
What do you mean functional? The important stuff, whatever that is, right? Yeah. So I hear you. I feel your pain. Yeah. Any other comments before I move on?
Well, actually, I have one. The one before that, the stuff that is hard to change.
Yes.
That kind of implies that there should not be any software architecture.
Right, so
just like there shouldn't be that basic reference.
By definition, Cabal is then software architecture.
Yes, by definition, it's so the stuff that is hard to change. A secondary, an implied point in that is I haven't strictly decided what's hard to change, right? Like at least in my experience, I don't know what's hard to change until we've built something real and have customers. And now I have to go change something and I discover it's hard to change. So it's disempowering, I think. It's somewhat in retrospect instead of a priori of the software project.
There's also here the first and second on this slide, they're also not necessarily the same because stuff's been made early, it doesn't necessarily mean it's hard to change or the other way around.
One of the things I've discovered just trying to look even quickly at software architecture is not to expect consistency.
Yeah.
I think that it's a nebulous concept, which makes, and then what we're doing here is even more nebulous because we're adding on to something nebulous. Okay, so far lightning talk's going great. I'm happy you're passionate. Okay, so I don't know, right? And what I like to do when I don't know is maybe try to define or generate some data to look at more deeply. And this is where I offer an example. And that example is the paper Build Systems a la carte. So I don't know what functional software architecture is, but I believe this is an example of it, right? I can't define it, but I think I know it when I see it. Now, Build Systems a la carte is, I think it's a 2014 paper by Markov, Neil Mitchell, and SPJ. And I just want to read this. This comes from its introduction. I want to read it to you. In this paper, we elucidate which build system properties are consequences of specific implementation choices, right? Blah, blah, blah. And how one can obtain new build systems with desired properties by recombining parts of existing implementations. Recombining parts of existing implementations sounds to me a lot like composition, but that's because I'm a functional programming diehard and addict and degenerate. As a compelling example, in section 5.4, we demonstrate how to combine the advantages of shake and base with carte. So moving on, in this paper, what they do is they use Haskell, of course, and they define basically an API for build systems. So this is their data types. They say, well, a build system is really some kind of abstract store, and it operates in response to tasks and all this stuff. All I'm trying to show is just to give you their entire spec fits on one slide. Right? It's one figure. It's really straightforward Haskell as far as the people in this room are concerned, I expect, right? But then, and this is where the functional architecture part really jumps out to me, is they go through this spec and they highlight, okay, well, I have some constraints and I have this new type tasks. And well, if I make task an applicative, this is the kind of build system I get. So they argue that Excel is a kind of build system, which I think is genius, describing Excel as a build system. And so if a task is applicative, well, then in spreadsheet 1, you only need applicative operations, and then that says that you can express the fact that the dependencies between cells can be determined statically just by looking at the formula, but you don't have to compute them. But wait, but if task is a monad, oh, well, now we can express dynamic dependencies, right? And so now cell C will depend on some other cell D, and we can express that dependency. But if task is a functor, well, I don't know, that's a degenerate case, but at least I have the spectrum, right? And then they go even farther. You have to read this paper. This talk could have just been titled A Love Letter to Build Systems a la carte, where they then map out the space of existing build systems in a table using this vocabulary of the space of build systems that they've built up, right? So, okay, so if I have a scheduling algorithm that's topological, they define that in the paper, go read it, and it uses a dirty bit, then I get make. If I have a scheduling algorithm that is suspending and I have a rebuilding strategy of deep constructive traces, then I get nix. So they argue. But I love this kind of idea, right? Like this, you're taking something, giving me an abstract specification, and now you're giving me a map of the territory, right? I'm oriented. So I want to say that that's the important stuff, right? This stuff is the important stuff. Knowing that I can get different behavior by different specifications of the kinds of functions I'm using to make my build system or my whatever system I'm architecting is the important stuff. The important stuff from this definition, important stuff, whatever that is. So maybe that if you accept a different definition of architecture, you have to argue that build systems a la carte somehow comports to that definition, but I use just the last one. So then I want to say, and here's my big leap of faith, right? Build systems a la carte studied build systems as an abstract concept using Haskell and Haskell's type system. And then I want to say, well, then what functional architecture is it is a way to architect systems by creating an algebra of components, which is what I believe build systems a la carte did. And then it used that algebra to describe the space of build systems. And I want to then make the further leap, if you'll trust me, that is expressing the essential complexity of build systems. And that's what I'm interested in with architecture. I'm interested in the essential complexity. Thank you for coming to my TED Talk. Yeah, go ahead.
Okay, two things. One is a stupid joke. So functional architecture is what architects do.
Okay.
And architects, you can just figure them out who that is by the job title.
Yeah.
And you can figure out if people as a function programmer by just asking them, one shut up about it. So that's so you go by that. But actually, something slightly with your system a la carte. So there used to be, I don't know, a long-running sort of fork joke or something that basically the way to do anything in function programming is to figure out how to see your problems that you're trying to solve as a mapping it to either writing a compiler or interpreter or something like that.
Yeah.
And basically algebra is sort of just a more dignified way to say the same thing.
Yeah.
So I think it's actually sort of in the folklore, it's the same answer the folklore gives you in a sense.
Yeah, I think so too, yes.
Okay, so going back to the things that are hard to change.
Yes.
By defining functional architecture this way, aren't you deliberately choosing to define it in a way so that it's less hard to change?
I can also choose not to accept that definition of software architecture.
Yeah, I get it, right? But this is, I don't like the stuff that's hard to change argument, as I pointed out earlier.
Okay.
So that like it seems like, you know, if you're gonna like, I mean, you're almost formalizing the, you know, your architecture if you want, like what you seem to be saying is that functional architecture is a formalizable architecture. It's a formalizable thing at a sort of higher level.
I want to believe. Yes.
Yes, right.
Yeah.
And if that's the case, then stuff that's hard to change is not the right definition of software architecture.
If that's the case, then maybe that's a good argument that that's a bad definition of software architecture.
And
but to play devil's advocate, I think the stuff that's hard to change is not the kind of functions that task is, but that there is a task type.
Oh yeah.
Right. They're like the components that are described here is the stuff that's hard to change.
To rescue the hard to change stuff of it, what architecture does decides what about your project should be hard to change, what should be easy to change. Ideally, for example, if you go to the passes on a carte, they make a few things that are easy to change, so you can go explore the state of the space of types of build systems relatively easily, and then you can move in that one easily. But it's hard to make a system that's buggy. Because if you start with something like make written in C, it's very easy to introduce a bug, but it's very hard to change a few things to turn it into shake.
Right.
And so basically architecture decides what should be hard to change and what should be easy to change. Maybe you can, if you want to rescue that sentence.
But there's a bit of a hindsight bias here, right? Because in this paper, you know, they look at all these existing build systems and they tease out the commonalities and they tease out what is the parameterization that allows you to instantiate, to create each of them as instantiations. But when you're originally writing make, I think the architecture of it is exactly that you box yourself into that top left cell. And if you want to move from there, it is going to be a very hard change because all these assumptions, they're not made explicit the way in the paper they are made explicit, but they permeate.
But what you see, they have a few gaps in their table of elements in the periodic table. They predict new type systems that some.
Sure. I mean, you can come up with new bases. What I'm saying is that this is an outside and after the fact view.
There's a recency bias, is how I would say it, or something like this. Some kind of bias.
I really think it's just hindsight because.
Hey, isn't that a good thing? Shouldn't we have hindsight?
No, I'm just saying that if you want to use this paper as a good source of definition for like software architecture, I would say that the architecture of any specific one of these build systems like make or XM, it does apply that the architecture is the thing that is very hard to change because if you wanted to change make to be like shake, to be phonetic, you
I see.
breaking the tunnel.
Yeah, so this suggests that there is a path to turn make into nix, but it doesn't mean that that's a path that you'll finish by the time you're done.
Yeah.
Yes,
But okay, let's say for the sake of argument that we were to re-implement make. Okay? But this time, with an awareness of that table, of that periodic table.
Yeah.
We would implement it in a different way, right?
yes.
Okay. So that we could like make small changes and turn it into whatever other build system we wanted. And it seems to me that what we're like architecture seems to me to capture the way that we would re-implement make. That is sort of the architectural difference between current make and this hypothetical make. And it's not so much it feels like there's something. I mean, we can make architectural decisions before we start implementing the thing, right? And so it's not only hindsight. It's
right here.
But
But here, we're not the fish, right? Like the fish doesn't know it lives in water, but we are not looking from the outside. But if you're writing your own stuff and you're not writing an N+1 implementation of make after having studied all these other build systems, but you're writing something that is like new or like unique, then you are the fish.
Yeah.
But you can of course go back and see what did we learn from writing make and whatever.
Yeah.
I'm wondering like how much of that is actually like dictated by the language or like the language that we decide to use, right? Because like
What is that?
so for example, like if we're using Haskell and we're using types and we're using the types to guide the implementation, then we're gonna have this very specific view of what's the high level. In the meantime, if you're using something, for example, object-oriented, that some things would inherently become easier, meanwhile other things will become much more difficult to change, and that's just by the choice of language. So kind of like the choice of API is partially dictated.
If you don't have higher kind of polymorphism, how do you even think about
Isn't it
this?
if you wrote this in APL, everything would be a matrix.
But there's an interesting thing about that one. So if you look at say either file systems or say you look at version control systems, if you basically write in something like C and you don't know what you're doing, you first end up with something like CVS, concurrent version system, and then like subversion. Stupid stuff like that. But even the C people eventually came up with something like Git. And Git is actually much closer if you look under the hood to something how you would write this kind of stuff in something like Haskell, because you have a graph and so on, the actual underlying concept. It just basically Haskell forces you to make decisions that that you only get after lots of painful experience when you write.
Yes, it constrains you towards a certain path.
And that's why I didn't pick C. Like I picked Haskell and I picked object-oriented because both of these are abstract, but they're abstract in different ways that make certain things easier.
Yeah. But I'm just saying that after you banged your head a long time with C or some object.
No, and that's why I picked two high-level languages. That's what I'm saying. I'm saying like these are two high-level languages that also make certain things easier or more difficult. One makes extending code sideways
but
harder.
it's eventually going there. Like for example, if you also look at copy on write file systems. If you know what that means. Even basically, so people designing those file systems, they still write everything in C, like a really low-level language. Where copy and write is not really the usual thing. As a copy and write is the copy and write plus garbage collection is the obvious thing that you do because
I'm saying,
definitely.
The argument you're making is like you implement stuff in low level, but you need some sort of high level abstraction. I'm saying the high level abstraction partially depends on like how you think, and how you think is dictated by if you're a functional programmer or if you're something else.
We ended up with functions because you're using a functional language.
I mean, partially. Maybe one could argue this is a good interface, high level interface regardless, but like if you're an object-oriented person, then the high level interface will make it more difficult to add maybe what's called what do you say, object-oriented? Yeah, so it would make it more difficult to, for example, add like extend your types or something like that, change your types.
You're talking about the expression problem.
Like as in like exactly. So to add more types of expressions, but it would make it easier to add instances or something.
Yes.
But I mean,
I think that's great.
Sorry?
I agree. I think that's a good one.
I think
but you can use these tools of abstraction to think about the problem, even if you then, after you've done it on paper, you plan to put that aside and use your acquired understanding to then implement it in a non-functional system, right? Like to think about the design of the thing.
Yeah, that's why I said that. Where was it? They used Haskell to study it. I guess I could have been more clear. But I wanted to say Haskell was a tool to study the concept and try to create the components, the abstract components that have to exist. Yeah.
So if we sort of change the example a little bit and think about something like a server, a client server architecture.
Right.
So if just going by your two examples, like a functional language versus an object-oriented language. But like my instinct, if I were to do a client server application in a functional setting, would to use sort of extensive use of higher order functions to allow callbacks and stuff. But the thing is, that's not very different from that you do callbacks in an object-oriented setting as well. And I'm not sure that the choice of language is really the thing that would define which of the two architectural decisions that you would make in that.
I just want to use existential types and modules and whatnot in Haskell just to emulate.
Can emulate objects.
Yeah. So there's something else going on, it feels like.
But then
Red paper for next year's functional architecture.
But then we're steering into the territory of you can program in Fortran in any language.
Yeah. You get to like the Turing target.
So I have an observation to make about make. So basically in the paper, I just looked at the paper, they describe make as having static dependencies.
Yeah.
Which if you see make sort of as the Platonic ideal, then yes, but the actual problem is that people take make, but then they tag on dynamic dependency in a really ad hoc and bad way. And they do that because basically they haven't really thought about the whole architecture and so on. If you have the hindsight of having this one, then you would see, okay, if you want to start dependencies, and instead of having like an applicative or something, we need to make our, for dynamic dependency, we need to have something like a model. Yeah. And then you can think about it and then even see how do we do that in C, translate back, but they didn't have that. So that it's all ad hoc and weird and recursive make and even worse stuff. So the problem is not so much like when you want to complain about make or some other systems, basically the Platonic ideal, but then once you want to do the extended, for example, you want to have dynamic dependencies in make, then it gets really ugly if you don't have a proper understanding of the system. That's it.
Yeah, I think this is kind of a tangent from what you said, but I actually think Marcus's paper on the functional UI that we saw before lunch is an example of this, because he's trying to recast, at least if I understand you correctly, Marcus, I think you're on Zoom, redefine model view controller frameworks as functional combinator, which seems it's very similar and is the kind of study that this paper did with It's just for MVC and in UI. So I issue a challenge to everyone in this room, like maybe we can find more data points and then we can keep the workshop alive. Yeah. Is there any questions on Zoom or no?
Oh, I can just.
When you say essential complexity, you mean the essential functional challenges or complexity as in like time, space sort of?
Not in time space.
Okay.
I mean, the essential complexity is defined in the paper out of the tar pit.
Right.
Yeah, which I don't remember.
The
accidental and essential complexity.
Thing. Yeah. So basically, this essential complexity, accidental complexity, and the accidental. That's the whole thing.
I see. So the stuff that's by design.
It's part of the problem you're solving.
It's part of the problem.
Things are hard to change for a reason.
Yeah. Like if you're going to parse something, you will have to read in chunks of data. You cannot avoid that. It's part of the problem.
Yeah.
Maybe that's fixed. Okay. Well, that's great.